Hey guys, in this video, I'm just going to take you through the last question of the HSC 2015 paper. I just want to make this video to show you how to get those final marks if you do have the time at the end of the exam, and show you how even though these questions are the most difficult ones in the paper, they are definitely still doable as long as you still apply your basic concept. But what makes them so difficult is sort of the algebra that can be involved with them at times, because you have so many variables going on. It can be quite confusing, but I'm going to take you through the solution and show you just how easy it actually is. So the diagram shows a cylinder of radius x and the height of radius y inscribed in a cone of radius capital R and height capital H, where these are constants. So it says the volume of the cone of radius R and height H is given by that. So that's like the generic formula of the volume of a cone, and this is a generic formula for the volume of a cylinder. So the first part of the question says to show that the volume of the cylinder can be written as follows. Okay, so the first thing we're obviously going to do is, we're going to take the generic formula for the volume of the cylinder, because that's what we're given essentially in the question, so why not use it? So the volume of the cylinder is given by pi r squared h. Now for this specific cylinder, the radius is x and the height is y. So we're going to replace our values of r and h with these values of x and y. So the volume of the cylinder then can be written as pi x squared y. Okay, now have a look at what we have, and having a look at what we need to prove, it's obvious that they've replaced the value of y with another value. So essentially they found y in terms of r and h. So that's what we need to do, and this is sort of the first hurdle you have to overcome for a question like this. So what you need to do is have a good look at the diagram. And the way that you form your equation is through realizing the similar triangles that are involved. So this triangle here and this triangle here, the small one over here. So I'm going to draw that on the side over here so it's more obvious. And I'm going to pop in the values that we have. So this distance here is x, this distance here is capital R. Now this small distance here is y. And the large distance is h, so that makes this distance here h minus y. Okay, so once you've established that, then you can sort of, find the corresponding sides in each triangle. So the small side x is put over the corresponding side in the larger triangle, which is r, and you do the same thing for the other side. So the small side now is h minus y, and you put that over the large side in the larger triangle, which is h. And now all you need to do is rearrange this equation to make y the subject. Okay, so now that we've found the value of y, now that we find an equation in terms of pi, in terms of h, r, and x, we can substitute that into the y over here. So we get v equals pi x squared of y, which is rh minus hx over r. And then we're almost there. All we need to do is take out h on r. H on r is a common factor. And so what we're left with is r minus x. Okay, so that's part one done. Now let's move on to part two. So it says, by considering the inscribed cylinder of maximum volume, so it's cylinder of maximum volume, show that the volume of any inscribed cylinder does not exceed 4/9 of the volume of the cone. So there's a few things going on here. The first thing you need to do is find the maximum volume of the cylinder. So in part one, we have the equation for the volume of a cylinder. So let's write it down here, h on r, pi x squared r minus x. Now we know to find the maximum, we need to differentiate and equate to 0. So that's what we're going to do. We're going to differentiate this function. So we get dv over dx. I'm going to leave h on r pi out the front because it's just a constant really. It doesn't really take part in the differentiating process. So what I'm left with is x squared r minus x. So this is differentiated using product rule because it's a product of two functions. So I'm going to differentiate x squared to get 2x, and I multiply that by the second function, plus the derivative of the second function, which is minus 1, times by the first, which is x squared. And now I'm just going to rearrange a few things and simplify the brackets. So I get 2xr, and I get minus 2x squared minus x squared becomes minus 3x squared. Okay, so that's my derivative. Now to find the maximum value, now to find the maximum value of x, we obviously need to equate to 0. So we say for max min, dv on dx equals 0. So I'm going to equate this to 0. Now I'm going to divide both sides by pi on r, on h, by h on r pi. So it's a constant, so it essentially gets eliminated. And what I'm left with is the brackets over here. So I'm going to factorize x. So 2r minus 3x equals 0. And then I get two values of x. I get x equals 0. And then I'm going to equate the bracket to 0 to find x. So 3x equals 2r. So x equals 2r on 3. So it's sort of obvious that x can't be 0, because if x is 0, then that will give us the minimum value, because that means there's no radius, so there's no cylinder. So we know that our value is going to be 2r on 3, but we need to show, obviously, that this is the maximum value. So you won't get full marks for this question if you don't actually show that this value of x gives you the maximum value. So it's really important. So you say show max min. Oops. And I'm going to show it using the second derivative. So I'm going to derive this again. So our first derivative was over here. So I'm going to get d squared v on dx squared. Once again, leaving my constant outside and differentiating what's inside. So I get 2r minus 6x. And then I'm going to substitute in my value of 2r on 3. So when x equals 2r on 3, d squared v on dx squared equals h on r pi, 2r minus 6 times x, which is 2r on 3. And I'm just going to shuffle this around and simplify it. So I get 2r, and these sort of eliminate, so I get minus 4r here. And then it's h on r pi. 2r minus 4r is minus 2r. Now, because we know that r is positive, h is positive, that means the minus 2 makes your second derivative negative overall, right? So it's less than 0. Now we've just proved that it's a maximum when x equals 2r on 3. So we say max when x equals 2r on 3. So now we have to sub that back into the volume of the cylinder to find the maximum volume. So if you recall from the previous question, we got the volume of the cylinder to be h on r pi x squared outside of r minus x. So we're going to substitute in our value of x into this equation here. So we get pi on r h, x squared is 2r on 3 all squared, and it's r minus x, which is 2r on 3. And now it's just a matter of algebra. So I'm just going to shuffle things around. So 2r on 3 squared becomes 4r squared on 9. And r minus 2r on 3 actually becomes r on 3. And just simplifying this, we get on the top, or one of the r's on the bottom here will cancel with 1 here. So on the top, we're left with 4 r squared h pi over 27. Okay, so this is the maximum volume of the cylinder. So let's have a look at the question again and see what we need to do next. So the question wants you to show that the maximum volume of the cylinder never exceeds 4/9 of the volume of the cone. So now we ask the question, okay, what is the volume of the cone? So we go back to the question here, and they've given you the generic formula for the volume of the cone. And we just replace R and H with capital R and H, just to be specific to this cone. So the volume of the cone was 1/3 pi r squared h. We need to show that this volume of the cylinder is no larger than 4/9 of the volume of the cone. So I'm just going to rewrite the volume of the cylinder in such a way that I sort of factorize out that 4/9, so it's a bit more obvious to me. So I take out 4/9, and what I'm left with at the top is obviously pi r squared h. But what I'm left with on the bottom is 3, because I've taken 9 from the 27. And what you realize is that in the brackets, what we have is actually the volume of the cone. We have that just over here. So we've essentially shown that the volume of the cylinder is 4/9 of the volume of the cone. And that's how you can show that since this is the maximum volume, it can obviously never exceed 4/9 the volume of the cone. And that's how you answer question 16. I really hope that helped.